First of all, I'd like to begin with some thank yous. I'd like to thank Andres and Inigo for inviting me, and I'm sure on behalf of the other speakers for inviting all of us to come here as lecturers. I'd especially like to thank all of you for coming and trusting us lecturers with 2 weeks of your time. That's a big chunk of time, and we hope it's worth it. I'm sure I'm not alone in putting a lot of work into it, but for it to really be worth it, we need you to put a lot of work, not just in listening, but in also just interacting with us over the 2 weeks. So how many of you are graduate students as opposed to postdocs? So some graduate students, and the rest are postdocs mostly, yeah? Those of us who are lecturing, the letters to us were addressed to professores, but let's forget students, postdocs, professor titles these 2 weeks. We're all colleagues. And in that spirit, even though there'll be lots of lectures, please don't hesitate with questions, especially in times between lectures, at lunch, on the open days, just to talk with us. Help us to become better teachers by giving us advice on what worked and didn't, but then, of course, bring to us any of your research problems that you think we might be able to help with. That's one of the most fun things about these kinds of workshops or conferences is the interaction. So please take advantage of that. So my lectures are going to be on the basics of Bayesian inference. So today it really will be pretty basic. We're going to talk about just the foundations and kind of the basic concepts. Some of you might already be familiar with this stuff. In that case, I apologize if I'm boring you, but not everyone has had this material, so we'll do the very basics today. Tomorrow, my lectures will be on mostly on a topic called Hierarchical Bayesian Inference, or multi-level modeling or graphical modeling, so slightly more advanced, but hopefully still accessible, and something of very broad applicability throughout astronomy. And I'll also talk a little bit about Bayesian computation tomorrow, but I'll focus on techniques that are mostly useful for low-dimensional models with only a handful of free parameters in them. These will be techniques that will be useful for you to know because they're good for transitioning between kind of conventional least squares or chi-squared or likelihood type thinking and Bayesian thinking. And then other speakers, especially Brendan and as well as Phil and others, will talk to you about much more sophisticated computational techniques like Markov chain Monte Carlo. All right, but before we get to all that fancy stuff, let's start with the basics. So first I'd like to start by establishing the context for these lectures, for this whole approach, Bayesian inference. Make sure this is working. So I'm starting with a quote here from a Cornellian. It's not in our contract, but we kind of have to always mention Carl Sagan when you come from Cornell. So this is a quote I very much like from Carl. It says, "Science is more than a body of knowledge. It is a way of thinking. The method of science, as stodgy and grumpy as it may seem, is far more important than the findings of science." Now that might be a bit of an exaggeration, but I think it is very good to emphasize the importance of methodology in science. It's what distinguishes scientific thinking, evidence-based thinking, quantitative evidence-based thinking from other ways of thinking about problems in the world, scientific or otherwise. One way I like to characterize the scientific method is that scientists argue. And by that I don't mean that we quarrel, though sometimes we do, including about statistics. But I mean we make paths of reasoning from some set of premises to a conclusion. We try to reason in some kind of rational, justified, objectively justifiable way. A key goal of science in particular, of course, is to explain or predict quantitative measurements, things we can assign numbers to. That's kind of the height of objectivity. And so data analysis, I like to view kind of one general way to phrase what it is it's constructing and appraising arguments that reason from data to interesting scientific conclusions. conclusions that try to explain something about the observable universe, or maybe our conclusions might be some prediction about some future observations. So the role of data in scientific arguments is not just to speak for themselves. This is sometimes a naive expression that you hear, is that it's to be objective, we want the data to speak for themselves. Data never speak for themselves in any interesting way. If they did, astronomy papers would just be tables of data, right? Here's a lovely quote by John Tukey, a very famous statistician, known especially for a collection of techniques called exploratory data analysis. And his statement is, no body of data tells us all we need to know about its own analysis. We don't just tabulate data, we analyze it. We gather data so that the data can speak for or against hypotheses. And in this picture of the scientific method as a kind of a rational reasoning from premises to conclusions, the data are part of the premises, part of the thing we take as given in our arguments. And we try to reason from the data with some kind of modeling context to hypotheses about the universe. So data analysis is a very broad area in all the sciences. And the part of it that we're going to talk about this week, Bayesian inference, I want to emphasize from the start, it's just a small piece of this whole big art and science of data analysis. And I just want to place it in context. And we're going to focus for these 2 weeks on this piece. It is an important piece, but I do want to emphasize that there's no claim that it's the whole picture. Even this kind of cartoon here I won't pretend to be the whole picture, but I like to kind of break data analysis into 3 different modes of operation. There's data reduction, which is taking the data, the raw numbers from our telescope or our instrument on a spacecraft, and trying to efficiently and accurately represent that information for subsequent analysis. There's exploratory data analysis, that area that I mentioned John Tukey contributed a lot to, and that's just ways to look at data to help us to generate hypotheses or to kind of qualitatively assess hypotheses before we try to do a quantitative analysis. That would include things like visualization, all kinds of graphical summaries, like different types of bar charts and stem and leaf charts, all those kinds of tools. And then there's statistical data analysis, which is kind of the most quantitative part that tries to make inferences or decisions about future experiments or come to the design of future experiments by taking data and building some kind of quantitative chain of reasoning. So that's what we're going to focus on, and in particular, we're going to focus on a piece of this balloon here, the Bayesian piece. So that's kind of the context. So Bayesian inference, what is it? So it's part of that blue bubble there, and it's a part that uses probability theory to quantify the strength of data-based arguments. So that's a more abstract view of probability than thinking of probability as describing variability in repeated experiments, which is the conventional view that we're usually taught, like in undergrad labs and things like that. One thing that is important to get straight early on is that you may know already of many kind of techniques in statistics, like you might have heard of least squares or chi-squared minimization or maximum likelihood. If you've gone beyond the basics, you might know about analysis of variance or survival analysis, or if this is a best linear unbiased estimation. Bayesian statistics or Bayesian inference is not just another one to add to this list. It's not just another method or class of methods to add to this list. It's an alternative to all of these things. For each of these things that you could learn about in a statistics course or text, there's a Bayesian version of it. So it's a bit of a parallel universe, if you will. So it's not just, one tool in this big toolbox that's what standard conventional or frequentist statistics is. It's an alternative to all of them. The focus when you're doing Bayesian inference is to state your modeling assumptions and try to derive consequences of them using the rules of probability theory. as I hope will become clear as the lecture proceeds, is it's a very different way of approaching a data analysis problem than the conventional frequentist approach, which instead focuses on trying to cleverly devise a procedure that you hand your data to and get a conclusion from, and then calibrate it, find out its variability properties. It's a very different way of working. As a result of that different take on the role of probability theory and that different style of working, the statements that one makes in a paper summarizing a statistical conclusion have a very different form in the Bayesian and frequentist way. So suppose we have some observed data set in front of us that we've got at our telescope or from our satellite, and we say the data, we argue, supports some particular conclusion, something about the sky. And how do we quantify the strength of the support? Well, in a frequentist assessment, you would say the conclusion was selected with a procedure that's right 95% of the time when applied to some big set of possible data, of which the observed data is one member. The Bayesian assessment would say the strength of the chain of reasoning from the model and the one observed data set to that conclusion is 0.95 on a scale where 1 is certainty. So this is a much more kind of abstract type of a statement than this one. This one is more abstract than it might appear in that it does refer to an infinite set of hypothetical data. So there's a somewhat illusory objectivity to this statement. But I just want to convey here, and it will become clear, I think, as we go along, that the kinds of statements that you make are very different. One thing to note here, and which we will see an example of in a moment, is that in the Bayesian statement, only the observed data appear explicitly for calculating the probability. In the frequentist statement, the probability involves some kind of averaging or calculating over many hypothetical data sets. So that's a very stark qualitative difference. The role that hypothetical or simulated data plays in inference is completely different in the two approaches. All right, so with that is kind of just the background, the contextual background. Now I want to get to kind of the main meat of the lecture, and the set of lectures that I'll give. And today in particular, it's going to be a bit of a meandering lecture, but I hope that it will be illuminating, at least for some of you, to take this somewhat meandering path. So I'm going to start by talking about a simple concrete problem, but then I'm going to go from there to kind of more abstract stuff and then gradually work our way back to the concrete. So what I'm going to talk about first is I'm just going to give a simple example of a frequentist result and a Bayesian result that will probably be familiar to most of you, though perhaps the derivations, in particular the frequentist one, might not be so familiar. And that's the idea of a confidence interval or a confidence region. Like if I need to estimate a parameter, the magnitude of a star, it's not that useful scientifically to tell you what's the best estimate without also telling you the uncertainty. The focus of Bayesian inference is really about quantifying uncertainty. So the main tool for quantifying parameter uncertainty in frequentist statistics is the confidence interval, like a 95% interval. The corresponding tool in Bayesian inference is called a credible interval. And I just want to give you an example. There won't be any formal derivations, but I want to convey to you, in the sense kind of Monte Carlo calculations, what's the difference between these two things, how they're calculated. Just as a kind of simple example to have in your mind, as then we go to somewhat more abstract stuff. So after that concrete example, I'm going to talk much more abstractly about the foundations of the Bayesian approach, which is based in logic, kind of back to Aristotle, thinking about deductive logic, but trying to generalize that to apply to inductive cases. So that will be fairly abstract, but we won't spend too much time on that. I just want you to know about that kind of background. Then I'm going to this will lead us to the laws of, or the axioms, if you will, of probability theory. Then we're going to use them to derive three theorems that are basically the core of the theory as needed for analyzing data quantitatively. this will still be, so we're gradually going to become more concrete. This will still be kind of abstract. We're going to talk about there being some parametric model that we won't express in detail yet. But just we'll have that in mind to derive these three theorems. And hopefully things will start appearing familiar here and a little bit concrete. And then we'll talk about how this applies to problems in estimating parameters in models or comparing rival models. And that's what I hope to get through in these first two lectures. And then in my last lecture today, we're going to apply this somewhat abstract theory to three concrete models: binomial, Gaussian, Poisson, kind of the holy trinity of probability distributions that appear in physics. And that's when things finally will become concrete enough that they'll actually be numbers. Okay. So, all right, so that's our meandering path, and we're first going to start with something concrete before the abstract, and that's confidence intervals versus credible intervals. So here's some ideas that hopefully will ring bells for you from your lab courses or from your early research. So suppose we want to estimate the mean of a Gaussian distribution from a set of samples. You can imagine repeated measurements of a non-variable star. And we want to estimate the magnitude, but also give an uncertainty. So we need a point estimate, that's the best value for the mean, and a region that somehow summarizes uncertainty. So here's the model. So each datum, if I knew the mean and the standard deviation of whatever noise is present, then the probability for observing a particular value of one datum is just this familiar Gaussian bell curve. In statistics notation, you write that this way: xi, twiddle, and then normal distribution with a mean and a variance. The statistics convention is to talk about a normal distribution in terms of the variance rather than the standard deviation. And this would be read, the probability for x is distributed like a normal with mean mu and variance sigma squared. So distributed as. And so for this problem, let's assume that the sigma is known. We have a well-calibrated instrument with some known noise level. We're only uncertain about the amplitude of the thing we're measuring, this mu. So it's important to distinguish the two types of variables in this problem. There's mu, which is a parameter. That's just a label that we give to different hypotheses about what it is we're observing. So a more general phrase for this is that mu defines the hypothesis space. And then a particular set of data values is a sample, and the sample space, if there's n data values, it's an n-dimensional space called the sample space. And then here are some standard inferences that should be familiar to you. So a familiar point estimate would be the sample mean, which I'm writing x bar, right? The standard error, the root mean square error, it would be sigma over root n for this x bar. A 1 sigma interval, that's horrible physicist terminology for the 68.3% confidence level, would be plus or minus sigma over root n, and then a so-called 2 sigma interval, which is about 95% confidence level, that would be plus or minus 2 sigma over root n, right? So all this hopefully is very familiar and almost trivial. All right, so now let's start applying this to simulated data and talk about what it means to say that this interval is a 95% confidence interval, for example. So suppose the true mean is 5 and the noise level is 4. And suppose we took 16 observations, so that 4 over root 16, sigma over 4, is 1. So sigma over root n is 1. So here I've plotted some simulated observations. Those are the blue dots on the x-axis here. And then the true value is the red line. That's at 5. And I've given you a confidence interval here. It's 5.5 roughly, plus or minus 2. So what's the confidence level that is associated with that interval? So it's of width 2, and you know sigma root over n is 1. So would anyone care to guess what the confidence level is? Probably you would guess 95%, right? That's 2 times sigma over root n. Actually, it's a 79% interval. So why is that? Well, I tricked you. If you were tricked by this, it's because you don't understand what a confidence interval was. And hopefully if you don't, you will by the end of the next 10 minutes. So on this slide, I show 2 different intervals. This one, 5.49 plus or minus 2, is the one I showed previously with a confidence level of 79%. This one here, which is 5.49 plus or minus 2, has a confidence level of 95%. If that puzzles you, again, let me say, that means you don't understand what a confidence interval is. And if you're in that category, I won't ask you to raise your hands, but if you are, what does that say about our discipline if every day we use something so simple and we don't understand what it is? We're actually, I have yet to see kind of a astronomy lab course or a physics lab course where they explain to you what a confidence interval really is, what it means. So let me tell you why these 2 numbers, even though these intervals look the same, why the confidence level associated with them are different. I actually used 2 different procedures to find those 2 intervals. For the green interval, this one up here that has the familiar 95% number associated with it, I just took the mean plus or minus 2 sigma over root n. But for the blue interval, I used a different procedure. I defined this thing. This is called the order statistic. X parentheses k means the kth ordered value of the data. So this would be x parentheses 1, 2, and so on, x parentheses 16. That's called an order statistic, any particular one of them. So I chose as my formula, my procedure for reporting a region, is I'm just going to report the region between the 6th and the 11th data. That is, I'll leave the 5 outermost on each side. That's a perfectly valid procedure. And for this particular data set, I cheated a little bit. I generated a bunch of data sets until I got one where the 2 intervals were the same to 3 significant figures. For this particular data set, this procedure gives exactly the same interval as this procedure. But the thing is, this procedure is right less often on the average than the green one. So that's why the confidence level is different for it. When I apply them to my observed data set, they give the same interval. But if I apply them over and over to many simulated data sets, they're right a different fraction of the time. So the moral of this story is that the confidence level is a property of the procedure, not of its application to a particular data set. And I try to make that point a little more clearly here. So now I've shown you 15 simulated data sets. And on the top of each one is the regular 2 sigma over root n interval that you're familiar with. And underneath is that blue interval that I showed you. And you can see a few interesting things here. One is that the green interval is always the same size. It's the 2 sigma over root n interval. Whereas the blue interval sometimes is bigger, sometimes is smaller. And then the other thing you could see is that the blue interval covers the truth. It hits this red dashed line less often than the green interval. In fact, 79% of the time versus 95% of the time. So this is kind of the Monte Carlo calculation you would do if you were trying to invent a confidence interval procedure that you're going to apply to your observed data. First, you generate lots of simulated data. You'd apply your procedure to it, find out how much of the time, what fraction of the time your procedure covers the truth, and that's the confidence level you would report. All right, so with that as background, let me go through a little more detail, but again, not a lot of equations yet. They'll appear soon enough, but mostly for kind of a Monte Carlo picture of how you formally would actually find a confidence interval for the normal mean. So this is that same setup that we just had. So here I've written down the likelihood function, which is the probability for all of the data. So probability for the entire set of data. We had 16 data points here. So that's a product of 16 Gaussians. And if you sum all the things that appear, all the terms that appear in this exponential, you get the familiar chi-squared statistic. Here it would be as a function of the one parameter in the problem, mu. So you can think of that mean procedure, that familiar procedure, is basically the simplest minimum chi-squared minimization procedure. And then we're going to use the likelihood curve, this thing as a function of mu, to define, we're going to learn how to use that to define a confidence interval. So this is, again, we're doing all frequentist statistics here. So here's how that calculation works. It's going to take us a few slides to get through it. So I'm showing here the sample space on the left and the parameter space on the right. And let me explain, this graph is going to appear a few times, so let's go through it. So remember the sample space, if you have n data points, it's an n-dimensional space. So let's think of a sample of only size 3 so we can visualize it. So here I've shown 2 dimensions. Actually, I'm thinking of samples of size 5, which are a little hard to visualize, but I'll try to show you a way to visualize them here. So samples of size 5. So what I've shown here in the usual orthogonal coordinates are the first and the second coordinates of 3 different data sets. Right? So I have one data set of size 5. Here is its first x coordinate and its second x, the x value of the first sample and the second sample. Then here's the second data set. It lands in a different place in this 2-dimensional subspace of the 5-dimensional space. And similarly for a third data set. Now in the bottom, I've introduced something that some of you may know about parallel coordinates. Have any of you heard about parallel coordinates or no? So with orthogonal coordinates, we run out of space with more than 2. We can try to show 3 with projection, but more than 3 is basically impossible to usefully visualize. So some statisticians and mathematicians have come up with this technique called parallel coordinates, where if you want to try to depict things in higher dimensions, just put the coordinate axes parallel to each other. So this first axis here would be like the, let me see, how did I do this? Yeah. So this first axis here is x1, x2, x3, x4, x5. So x1, this green point, there's its value. The blue point, there's its value. The red point, there's its value. Now, for the green point, x2 was a little less than -1. So here's its second coordinate point. And similarly for blue and red. So the trick to getting parallel coordinates to work is that a point in the 5-dimensional space now becomes something called a polyline in parallel, a polyline in parallel coordinate space. So this green segment connects the 5 coordinates of that green point, that 5-dimensional green point. So points become these polylines. It's just a way to be able to show on a piece of paper or a slide a high-dimensional object. And if you really get into parallel coordinates, there are certain patterns in parallel coordinate space that correspond to interesting geometric structures in orthogonal space. And if we were doing a course on that, I'm not an expert in them, you'd learn about all those. There's entire books on this. It's a very popular high-dimensional visualization technique, but I just wanted to give you the gist of it here. I just wanted to find some way to show you, several 5-dimensional points. All right, now up on the top right, now we're looking at parameter space, the mu space, and I've plotted here the log of that likelihood function. So minus chi-squared over 2 as a function of the unknown mean. So there are several curves here, and imagine I've drawn these with a true value of mu of 0. So here's the curve for each of those 3 data sets, and here's the point where the true parameter value, the likelihood for the true parameter value. Now, I'm going to try to use these curves to generate a confidence interval. So I want to find some recipe to go from this curve to a region of the mu axis. And the standard recipe is as follows. First, you line up all the curves so that they have the same peak. In other words, you look at the change of the likelihood from the maximum likelihood value. That's this delta log likelihood. So what here I subtracted off the peak value, so it starts at 0 and becomes negative. And so here are those same three curves, but now just shifted. And here are the likelihood values of the true value of mu, 0. And on the right, I've plotted those 3 points, and I've imagined trying to build up a histogram in this horizontal direction of where those points are. Now, it's not so obvious yet the histogram has that shape, but suppose now instead of 3 data sets, we simulate 100. So here are the 100 data sets, their first 2 coordinates. In parallel coordinates, here are all of their dimensions. For each one of them, we get a likelihood curve. Their peaks are all over the place. But if we line up the peaks and we look at where the likelihood values of the true coordinate value are, then we get this kind of a histogram. I plotted the points here are all these colored points right at mu equals 0. And this is just a histogram of them. So now we can imagine coming up with a recipe where we're trying to come up with a recipe that has some known probability of giving us the right answer. If I want, say, I think I drew this red area as for a 68% region, I just go down in likelihood enough so that 68% of the time the change in log likelihood is smaller than that amount. If I choose that amount of change in log likelihood here, it's a half. Then if I take my likelihood curve, go down a half, and use that to define a region, I know that 68% of the time it will include the true value, assuming here that the true value is 0. Of course, I don't know what the true value is. Maybe the true value really was 3 or some other value. So I really should do this for all possible true values, because I don't know what the truth is when I have a real data set, and see if that histogram looks different depending on what the true value is. In general, it does, but a magic property of the Gaussian is that this distribution of delta log likelihood has exactly the same shape no matter what the value of the unknown mean is. This is actually a very important property. It's called, it means, in statistics lingo, this is expressed by saying that the change in log likelihood is pivotal. That means its distribution has a shape that doesn't depend on knowing the truth. That's crucial in frequentist statistics because you never do know the truth. That's why you're doing statistics. So you want to try to find procedures whose properties don't depend on you knowing what the truth is. They're rare, but at least approximately you can sometimes find them. So this probability, the probability of being right, this fraction, this red fraction of the histogram is called the coverage of the interval. The confidence level is the maximum coverage over all possible values of mu, but since here the coverage is the same for every mu, the coverage and the confidence level are the same. That's a detail I don't expect you to follow right here, but it's something statisticians worry about. Now there's a technique you might have heard about called Bootstrap confidence intervals. What we've done here is something much like the parametric bootstrap. I just want you to know that there's some connection between this phrase bootstrapping and this kind of Monte Carlo calculation we did. In particular, the parametric bootstrap just doesn't worry about whether, how the shape of this changes for different values of the truth. It just plugs in for mu the best fit with the actual observed data. So kind of using the best fit as a surrogate of the truth, and would only do the simulations for that one data-dependent value of mu. It's officially cheating from the frequentist point of view, but the theory, what makes the bootstrap so interesting to statisticians is the theory shows that it's approximately right with the kind of a controlled approximation. All right. So having done all of that with Monte Carlo simulated data, now we go back to our observed datum. Say it was this data point here, represented by this polyline, and we just find its likelihood curve and go down a half, find whatever interval that hands us, and then we report that region, but with a coverage, a probability that we've calculated from looking at lots of simulated data. The hypothetical data. All right. So that's what you've done. Whenever you've calculated a sigma over root n kind of interval or reported a 68% or a 95% confidence region, whether you knew it or not, you either did this calculation or you relied on somebody else having done it and told you that that was the particular confidence level to use. So now, how would you go about this from a Bayesian point of view? So I'm not going to derive where all this comes from. That's the whole topic of the rest of these lectures. But I just want to show you mechanically how it's different. So recall that the likelihood function, this function of mu, the probability for the observed data as a function of the unknown parameter, it's a probability for the data, not for the parameters. The parameters appear to the right of this. It's a probability for data, not parameters. So there's something that will be familiar to many of you already, but if not, you'll learn about it in the next hour or two. Bayes' theorem is a way to convert between, it's basically a way to reverse the order of these things, to convert from P of D given mu to P of mu given D. It comes from the product rule of probability theory. Let's not go through this now. We're going to go through this in detail soon. But roughly speaking, the recipe is basically that you look at this curve and you marginalize it after some possible weighting over mu. I mean, you normalize it. And then you can think of it as a probability distribution. It's called the posterior probability distribution. And it requires some kind of, at least formally, some kind of weighting, which might just be constant as a default choice. So what would that look like in this problem? So remember the likelihood function was a product of these exponentials. It also had normalization constants out front, but they don't depend on mu, so we don't care about those for the at the moment. So it's a product of these Gaussian shapes. Now an exercise we'll do in about an hour is to complete the square in this, and you can show that this thing is proportional to a Gaussian in mu, located at the sample mean, and with width sigma over root n. So that's an algebraic exercise that we will do explicitly in a little while. So that likelihood function, we plotted log likelihood curves. They look like parabolas. In fact, they are parabolas exactly, this parabola. With a flat prior, if we try to then normalize this thing, we would get a 1 over root 2 pi sigma over root n normalization constant. It would just be a normal distribution with mean at x bar and with a variance sigma squared over n. So this is what the Bayesian calculation looks like in that same sample space parameter space description. There's the observed data, which is a point in the 5-dimensional space, so one point in this 2-dimensional projection, or one polyline in parallel coordinates. Here's the log likelihood function. What we want to do is take the actual likelihood function, exponential of this parabola, and normalize it, and that gives you this Gaussian distribution. And for our region, we just integrate under that. We find the smallest region, or the region of highest density that has 68% probability, and that's this red region. So that's the Bayesian calculation. And what I hope this conveyed to you, if nothing else, is just that these two calculations are incredibly different. It so happens for this problem, they lead to the same answer at the end. The sample mean plus or minus sigma over root n. But I hope this figure versus this one look very different to you, right? Totally different calculations that happen to give the same answer. So the rest of these lectures are largely about why to do the calculation the Bayesian way, what possibly justifies that, and then what are the consequences of doing that. But we can already say something about when the two results might differ. I mean, it should be clear that the math was very different. Therefore, the fact that the answers are the same had to be a mathematical coincidence. It is, and it doesn't happen in general. So what are some of the scenarios in which the two results will be different? Well, not all frequentist procedures use the likelihood function directly, just by plotting it and using it to get intervals. If they don't, then the Bayesian and the frequentist result may be different. I mentioned that the shape of that delta log likelihood distribution didn't depend on the true value of mu. Well, in general, it will, especially if you have nonlinear models or if your errors are not Gaussian. When that's the case, then frequentist and Bayesian results will tend to differ. If the actual shape, so one of the interesting things about that Gaussian problem, every one of those likelihood functions for a simulated data set was exactly the same parabola, just translated. Right? That, too, is a very special property of the Gaussian distribution. In general, if you look at the likelihood functions from different data sets, they'll have different shapes. When that's true, then frequentist and Bayesian results tend to be different. A big focus of what we'll talk about later in these lectures is that in many problems there are extra uninteresting parameters called nuisance parameters. Like I'm trying to estimate the magnitude of a star, but there's a background. There's bias in my CCD. There's background from the night sky. It's uncertain background. I have to measure it, propagate its uncertainty somehow. When there are uninteresting parameters, it turns out that in general, the way you try to account for their uncertainty makes Bayesian and frequentist results different. And then finally, there was this weighting term in front, this so-called prior. If there's important prior information available, there's one unique recipe for how to use it from the Bayesian approach, but not so much for the frequentist approach. So these are all things that make the two answers different. So this is just to say that even though in this simple textbook problem of the normal mean, and there are a few other examples, Poisson counts and binomial counts, the simplest textbook problems, the two approaches give the same answers usually. But those are just mathematical coincidences that are just properties of some simple distributions. And in general, the answers will be different. So the message here is that you have to make a choice. You can't just think, well, I'll just do it because they all agree. And it's just really a matter of, some philosophical argument about the meaning of probability. No, the philosophical stance you take on what to do with probabilities leads you to do actually different numerical calculations that will give you different answers in general. So you need to think about the choice. Think about what the different approaches are trying to accomplish, which one addresses your scientific question most directly, and do that one, because whichever choice you make, the answer will be different. So you want to try to make a reasoned choice based on knowing about both methods. All right. So this was a one-dimensional confidence region. Now there's a lot more to the kind of basics, fundamentals of Bayesian inference than I could hope to teach you in 6 hours. And so on the website where you'll have all these slides, I'm also posting a supplement set of slides, and there'll be a few topics that will come up in the next few hours and tomorrow that I'll mention are in the supplement. And one of them is doing this in multiple dimensions, and it's just telling you the difference between parametric bootstrapping and posterior sampling, something we'll learn a little more about tomorrow and afterwards. If bootstrapping is something you've done or think you should know about, but you're curious about the relationship between that and Bayesian methods, then you might want to have a look at that. And if it looks interesting, it probably won't be understandable without me talking about it. You can ask me about it. So that's a supplementary topic. I raise it because the bootstrap idea, if you know a little bit about it, oh, thank you. Thanks, Andres. The bootstrap idea is an appealingly simple idea, but almost more than any other kind of general statistics approach I know about, astronomers do it wrong. And so part of those slides in the supplement are that if you decide you want to do bootstrapping, at least do it right. So part of those slides are just to show you how to do it right from the frequentist point of view, right? And then also to make the contrast to see how it relates to the Bayesian point of view. Okay. I have some remarks here. Let me think if I want to spend the time. Yes, okay, let me just say some. So I tried to make the point to you that you have to make a choice. The two methods are different. Now you're hearing that from an astronomer, but I want to give it more authority. So I want to give it to you in the words of two very famous statisticians. So Brad Efron, he's the inventor of the Bootstrap. Really smart guy, and a friend of mine, and somebody who's very interested in astronomy. He's made some contributions to statistics in astronomy. Very much not a Bayesian, or not in favor of Bayesian, purely Bayesian methods, but influenced by them. And so this is a quote. He was a former president of the American Statistical Association, the ASA. This is just a quote in one of his recent papers, talking about the Bayesian frequentist debate, emphasizing that it's unusual among philosophical arguments in actually having important practical consequences. They don't always give the same answers. So it's not just some renegade astronomer telling you this. It's one of the foremost statisticians of our age, trying to make this point. Roderick Little, so another very famous statistician, but more from the Bayesian side. I wanted to give you kind of two sides of this. He gave the ASA President's Address in 2005, a really nice paper called The Calibrated Bayesian Viewpoint. And again, makes the same point. The Bayesian and frequentist philosophers can differ even on simple problems, and he advocates this approach that we won't talk too much about here explicitly, but it's worth knowing the phrase, at least in your head, that his so-called calibrated Bayes approach uses the Bayesian approach to address inference, but then uses frequentist ideas to try to fill in some holes in some of the arguments. Like if there aren't strong arguments for priors, let's take the Bayesian approach and think of how a frequentist might just use it as a procedure, and how well calibrated it would be from a frequentist point of view, and let that influence our choice of prior. Or especially a lot of Bayesian statisticians, Little and Andrew Gelman, for example, like to use some frequentist ideas to influence checking the quality of models, rely on Bayesian techniques once you've chosen a model to do all your inference, but then rely on some frequentist ideas, not the actual kind of formal theory, to guide your what they call model checking, Bayesian model checking or model assessment, adding to the frequentist ideas some Bayesian ideas for how to account for parameter uncertainty. Anyway, I just wanted you to know it's not just an astronomer saying these things. These are things that are recognized in statistics literature. All right, so hopefully that was somewhat concrete. I mean, I showed you Monte Carlo simulations and things like that, but now let's get abstract. So we'll get a start on this, and we'll take a 5-minute break and then pick up the rest of it till the end of my first couple of lectures. So I want to talk about kind of the conceptual foundations for the Bayesian approach, which is logic and viewing probability theory as an extension of deductive logic. So why talk about logic? Well, I tried to make the point early on that the scientific method, nobody agrees on exactly what it is, but I think we can agree that it has to do with patterns of constructing arguments, building arguments that reason from quantitative data to quantitative conclusions about the world. And if you open a logic book, I just opened a fairly popular one here, logic can be defined as the analysis and appraisal of arguments. So that is an argument, if you will, that logic should be relevant to thinking about the scientific method. In logic, you build arguments with propositions, just statements that might be either true or false. You might not know enough to say whether they're true or false, but the statement is either true or false. And you build an argument by connecting propositions with so-called logical operators or connectives. So a proposition, as I said, a statement that might be true or false. And I just give some examples here. So the universe can be modeled with a lambda CDM model. That's a proposition. Either that's true or false, that the universe can be accurately described that way. Within the context of such a model, here's a proposition that the total matter and energy density relative to the critical density is in this interval, 0.9 to 1.1. That's either true or false in the context of this model. Here's another proposition. Omega lambda is not 0. There's some dark energy. That's a proposition, true or false statement. Then there's this symbol here, B bar, or some people denote it with a twiddle B. That's not B, or the denial of B. So if I deny this statement, then I'm asserting that omega lambda vanishes. So that, too, is a proposition. So connectives are things that, ways to join more than one proposition. So a wedge is the statement and. We would read this A and B, and it means that both the propositions A and B are true. And then V, A, V, B, we would read A or B. This new proposition is true if either A is true or B is true or both are true. So an argument is an assertion that some conclusion, let's call it H for hypothesis, follows from some premises, some set of other propositions that we're going to take as having their truth given or established. So P for premises, which could be a list of, this is basically an and. It's saying all these things are considered to be true. And so let's use the following notation. It's not quite standard for arguments. We'll use this H bar P to say that the premises imply the hypothesis, or just different equivalent ways of reading this symbol. H may be deduced from the premises. The hypothesis follows from the premises. The hypothesis is true given that the premises are true. An argument is itself a proposition. It's a statement that H follows from P, but it's a complicated one. It's built from other propositions. Because arguments are kind of the main thing that we want to talk about in logic, there's a special terminology for when an argument is true or false. A true argument is valid. A false argument is invalid or fallacious. Now, it's worth understanding what we mean by valid and invalid. So there's a difference between a valid argument and a sound argument in logic. Now, so I'm introducing some terminology here from logic. An argument is said to be factually correct if and only if all of its premises are known to be true. So everything to the right of the bar, if you know for certain that it's true, then the argument is said to be factually correct, regardless of whether the hypothesis follows from it or not. You're just saying that the premises are right. The argument has good content. An argument is valid if the conclusion follows from its premises. So the statement that H follows from P can be true whether or not P is true. That's what validity refers to. An argument is sound if it's both factually correct, all the premises are true, and it's valid, that there is a rational path of reasoning from the premises to the conclusion, the hypothesis. Is that clear, those distinctions? So there's a difference between, the key difference is between soundness and validity. An argument is valid if you can get from the premises to the hypotheses, but the hypotheses might still be wrong if one of the premises is wrong. An argument is sound if it's valid, but you also know that all the premises are true. In that case, then you know the hypothesis is true. So deductive logic, as a formal mathematical symbolic theory that lets you derive things, it only addresses validity. And as we'll see in a bit, statistics, Bayesian or frequentist or whatever else, essentially also only addresses a kind of validity. Really what we want to do in science is we want to make sound arguments. We want not only our path of reasoning to be valid, but we want the premises also to be true. It turns out, at least so far, there's no formal approach for addressing factual correctness. So there's always a subjective element to arguments. Logical arguments, statistical arguments, frequentist, Bayesian, I don't care what. nobody has a theory yet, even a good candidate theory for how one establishes, I mean, philosophers even argue what it means to say certain types of premises are true, right? In particular, if you go to a logic book, and here are two very well-known ones, they basically say it's the job of science to establish factual correctness here. Logic can teach us something about validity, but very little about factual correctness. That's a subject matter of the sciences. Or here, Copy, one of the most famous books, the test the truth or falsehood of premises is the task of science. Well, that's not very comforting. So the bottom line here is that scientists who try to think deeply about science, including philosophers of science, try to look at philosophy, including logic and inductive generalizations of logic, to try to address factual correctness, whereas a logic book says, well, look for the sciences to establish factual correctness. So there's no way to deal with this. So all we can talk about in any formal way is validity or something like validity, and that's really going to be our focus. And when we try to mathematize, the strength of arguments, we're really only going to be talking about validity. That's the only thing we can quantitatively address. So we're going to have to just take the premises as given at some level. But let me give you some examples of the types of premises we might deal with. There might, in fact, be things that are facts, things that are known to be true. Foremost among the facts that we have are our observed data. We know that there were 100 counts in this particular pixel of the CCD, right? Or we know that the bolometer measured, so much energy on this particular pixel of our infrared camera or whatever. The data are one of the few things that we have that we know are true. Almost everything else starts having shades of truth that among the premises. So there's kinds of a scale of truthfulness in premises that's at least worth knowing about in the back of your head. So besides the brute facts, which are data, we might have assumptions. And I give as example here premises from geometry, because you probably all learned some geometry in high school or even before. You might remember learning Euclidean geometry, the stuff with compasses and rules and theorems about triangles and parallelograms and parallel lines. You might remember that Euclidean geometry has 5 postulates. So Euclid considered his first 4 postulates to be obviously true. They were statements like, between 2 points there can be one unique line segment, straight line segment. Or that right angles are congruent. So if there are 2 right angles, you can rotate one of them to perfectly match the other. He considered these things to be obvious. And in Euclid's Elements, where he derived, hundreds of theorems in geometry, the first section was devoted to the theorems that required only those 4 obvious postulates or axioms. It was a rather short section of the book. Sometimes we have to introduce premises or statements to reason from that seem reasonable, even though we might not be totally sure of them. So in Euclid's Elements, there's the 5th postulate, that parallel lines never meet. Right? Euclid was troubled by this one. That's why he kept the first part of the book separate from the second. But it turned out he needed this postulate in one way or another to prove most of the interesting theorems of Euclidean geometry. We now know that this postulate does not follow from the other 4. You could have made other choices here that lead to different geometries. And in fact, we think the real world is a non-Euclidean, corresponds to a non-Euclidean model. You might, in trying to formulate an argument, just not be able to get anywhere with the premises that you're comfortable assuming. So then you just have to make another assumption out of desperation, just to go on. Desperate presumption is what I have here. So that's kind of the scale that you might have of comfort with premises. But another important point to make is that if I've already built a sound argument or a valid argument previously, I can use the conclusion of that argument as the premise for a subsequent argument. So, and build chains of arguments. And really that's what science is about, chains of discovery where we link together lots of different discoveries. And this happens very explicitly sometimes, for example, in cosmology, where you take like inference about H naught from the Cepheid observations and use that as a input to an analysis of a cosmic microwave background or large-scale structure model. And then so you're building a chain of discovery where you're taking, you know, an argument about H naught from one set of observations and chaining it into an argument about other parameters like lambda from another one. So every argument has some set of premises, and the premises we have to consider given, if only for the sake of the argument, if you will. Let's distinguish between two types of inference. There's deductive inference, which is really the subject of classical logic, and the prototypical deductive inference is a syllogism. So just schematically here, if I take as a premise that A implies H, and then as another premise that A is true, then I can deduce with certainty that H is true. Another way to put that is that this argument that H follows from these premises is valid. That's the subject of deductive logic. There are entire books and courses you can take on that, and there's lots of interesting things you can do with this. But arguably the most interesting things, certainly most of the topics of science, cannot be put into this deductive framework. A lot of the most interesting types of reasoning we do are what would be called inductive reasoning. And there are many types of forms of inductive reasoning, but here's one kind of prototypical type, which is reasoning by analogy. So, for example, a premise might be that these 5 different objects, A, B, C, D, and E, all have these 3 properties, X, Y, and Z. Now I have a new object, and I observe it, and it has properties X and Y, new object F. Inductively, I might argue that since everything I know of that has X and Y also has Z, I'll infer that F has that property Z. This is not a strictly valid argument, but it might still be rational depending on exactly what these objects and properties are. You could probably imagine situations where this might seem like a strong argument and others where it might seem weak. So exactly how strong this argument is will depend a lot on the actual content here. So there are ways to mathematize these two different types of arguments. So symbolically, you can convert deductive arguments into an algebra over the numbers 0 and 1. This is a set 0 and 1, and that algebra that corresponds to deduction is called Boolean Algebra, and you may have learned about it if you ever took a digital electronics course. You learned about Boolean Algebra. In a very close analogy, probability theory from the Bayesian point of view is a very similar algebra corresponding to induction, but where the algebra is not over the two numbers 0 and 1, but over the whole real interval from 0 to 1. So here's what that algebra looks like. Here are kind of the laws or the rules of the calculus over that algebra. You think of this thing called probability in the Bayesian approach as the strength of the argument from the premises to the conclusion, the hypotheses, where 1 means that the argument is deductively valid. That would be the ideal. 0 means that, in fact, the premises imply the denial of H. But then all the numbers in between are some kind of, degree of deducibility, if you will, or degree of validity, a strength of this argument. And we'll say a little bit more about how to interpret that in a bit. And so the mathematical model for induction that is probability theory is a set of rules for combining numbers on this scale. And in mirror to logic, where in logic it so happens that if you have rules for and, or, and not, then you can deduce anything. Similarly, in probability theory, if we come up with, a kind of calculus for and, or, and not, then that's all, it turns out that's all we need to know. I'm not deriving that, I'm just telling you that. I'll say a little bit about how that can be derived in a minute. But So here are those rules that the probability for A and B being deducible from P is the probability for A being deduced, the strength of the argument from P to A times the strength of the argument from P supplementing it with A to B. And then on the second line here, I've done the same thing, just reversing A and B. The OR rule says that the probability of either A or B following from your premises is the sum of their separate probabilities that they would follow from the premises minus a kind of double counting term. You've probably seen all these things before. And then there's the NOT rule, which is just that the probability for that the denial following from the premises is 1 minus the probability of the conclusion itself following from the premises. So I just argued that that kind of calculus of probabilities by analogy to Boolean algebra, and arguments somewhat along those lines are what were originally offered when probability theory was first being developed in the 1700s and 1800s by people like Pascal and Laplace and Gauss and de Moivre, those people. There wasn't Boolean algebra at the time, but they knew how to reason logically, and they viewed probability theory as a generalization of logic. Today, there's now formal ways to derive those three rules from kind of more basic qualitative desiderata, if you will, of theory. We're not going to go through any of those. I wrote a paper long ago reviewing one of them due to Cox and Janes. Phil's book gives a nice summary of this if you don't want to go through all the detail offered in Ed Janes's book, where you can make this analogy that I just made very precise. But there are other qualitatively different approaches that all lead to this same algebra over strength of arguments. One is how would you try to coherently bet over things that you're uncertain for? How would you choose the odds to accept or not to accept when you're making bets on things you're uncertain for? Well, it turns out if you want to be sure that you're not guaranteed to lose, then the odds or ratios of probabilities have to follow exactly the algebra that I just outlined for you. And there are other derivations from other criterion. There's an information theoretic derivation that leads to this same kind of algebra. There are also some well-known and well-acknowledged limitations of frequentist reasoning. And there are some theorems that show that to avoid a few of those, one called recognizable subsets, another called stopping rules, that you have to do something like this algebra. So this is just to say that algebra that calculus, those set of rules that I just gave for you, they're not just something arbitrary. There's actually something really compelling about those rules. No one of these arguments for those rules may appeal to you, but the fact that they all lead to the same place is pretty suggestive that there's something to this. All right. And so we're going to take a break in a minute, but I just wanted to leave you with just a few statements from some of the founders of the early founders of probability theory applied to data analysis. Making the point that they viewed probability theory as kind of a mathematization, if you will, of just reasoning, logical reasoning. So Laplace famously said probability theory is common sense reduced to calculation. Maxwell said very clearly that logic only deals with things certain or impossible, entirely doubtful. The true logic of the world is the calculus of probabilities, which is a generalization to that over the whole scale between impossible or known to be true. And then Harold Jeffreys, who's one of the main people who started to revive interest in this Bayesian approach of Laplace and Maxwell and others in the mid-20th century, said that it's a kind of relation between data and consequence. So just making the point that historically this was the way people looked at things. All right, let's take a break there and a little 5-minute bathroom break, and then we'll come back, pick up from there.